Okay, so let's try and work out how hot this mysterious X-ray source, Scorpius X1, must be. Now we know that if something is emitting like a black body, then the peak wavelength is going to be equal to a constant, which is roughly 3 by 10 to the minus 3 divided by the temperature. What wavelength are these things emitting? Well, they emit all the way out to X-rays. Let's say X-rays of about 10 kiloelectron volts in energy. For photons, the higher the energy, the shorter the wavelength. So short wavelength photons pack a big punch, whereas long wavelength ones like radio waves are very weak. So this energy corresponds to a very short wavelength, about 10 to the minus 10 of a meter. 0.1 nanometer, about the size of an atom. Which is indeed why you use X-rays to study atomic structure and crystalline structure. So, if we plug this wavelength into here, we can rearrange that, we get T equals 3 by 10 to the minus 3 over 10 to the minus 10, which comes out as a whopping 30 million Kelvin. So that's 3 by 10 to the 7 Kelvin. So, wow, that's hot. I mean, the sun at 6,000 degrees is positively icy in comparison. But that poses a problem. If it really is that hot and is radiating as a black body, then it must radiate an absolutely staggering amount. If you remember, the Stefan-Boltzmann equation tells you that the energy power radiated per unit area is equal to area times the Stefan-Boltzmann constant times T to the 4th power. And as our temperature is so enormous, that's going to be absolutely colossal. So the power per unit area is going to be absolutely staggering. Which means that probably the object has to be quite small. If it had a very big area, say as big as a red giant star, and also a temperature this high, it would be blindingly bright even by day. It is a very, very bright source. Emits enough X-rays to appreciably ionize the upper atmosphere, but it's not that bright. The luminosity, in fact, is about 2 by 10 to the 31 watts. You can determine that by looking at the X-ray flux and factoring in the distance by the normal inverse square law equation. So given that luminosity, we know that that must equal, if it's a black body, a sigma T to the 4th. So we know that L equals the area. If it's a sphere, that's 4 pi r squared. Sigma, the Stefan-Boltzmann constant, which is 5.67 by 10 to the minus 8, times T to the 4th, and we know the temperature up here. So from this we can work out the radius of this object, again assuming it's a sphere. So what we can do is we get that r squared equals L over 4 pi sigma T to the 4th. Take the square root of both sides and we find that r equals square root of L over 4 pi sigma T to the 4th. And if we plug in the temperature, 30 million degrees, Stefan-Boltzmann constant, 5.67 by 10 to the minus 8, and the luminosity, 2 by 10 to the 31, that comes out as roughly 6 kilometers. Not 6,000 kilometers or 600,000 kilometers or 6 light years or 6 astronomical units, 6 kilometers, in the size of a suburb. So, whatever these things are that are emitting this huge amount of X-rays, they must be extremely small.